Bismillahirrahmanirrahim. My name is Jahangeer Soomro. I am Assistant Professor at Electrical Engineering Department, Sakhar University. Currently, I am doing PhD from my own university, Sakhar University. Today, I will present summary of one of the research papers named Circulating Current Reduction in MMC HVDC System Using Average Model. Basically, MMC is considered to be an invincible topology for the applications of high voltage direct current HVDC and multi-terminal DC MTDC grids due to having silent features such as modularity and scalability. There is no need of filter at the load side, improved power quality, reduced harmonic content. It has inherent fault blocking capacity, and moreover MMC also have one more advantage, that is it has inherent energy storage capability which can be used for power oscillation damping. So considering these all features, MMC is considered to be an attractive topology for medium and high voltage applications. However, for a large DC network, MMC requires a large number of submodules and switches, which makes its modeling very challenging and computationally complex using EMT programs. This is true. If we talk about detailed switch modeling, first we need to understand that as per Sigree there are 7 types of model. The first type of model is detailed switching model. In detailed switching model, we take hundreds of cells and thousands of switches to model basically MMC. Now, detailed switch modeling is considered to be most accurate and is used as a reference model to validate other models. It accurately represents the switching dynamics. But the drawback of detailed switch modeling DSM is that it requires higher computational burden and it reduces the simulation time step. So EMT simulation slows down if you use detailed switch modeling. To overcome these drawbacks, researchers are looking for more efficient yet simplified and accurate models to replicate and model the behavior of MMC. So one of these models is average model or aggregate model, which is used in this paper. As compared to DSM model, here in this model it will have reduced computational burden and increased simulation time step. So simulation time will be faster in this average model. Alright. Average value model provides a relatively better solution to model MMC by combining cells as an arm equivalent circuit. Circulating current is an important issue related to performance and stability of MMC. This is very true. MMC produce circulating currents. Circulating currents possess second order harmonics which causes ripple and unbalances in capacitor voltages of the output of the submodule voltage. So if these second order harmonics are not controlled properly, they will trigger towards fourth harmonic and onwards, and this will result in overall increase in the TAD. This will result in overall increase in the power losses, increase in the RMS current of the arm currents, and overall the system may move towards instability and failure. Therefore, circulating current must be suppressed and capacitor voltage ripple must be reduced. The traditional method for inserting submodules in each arm is based on direct modulation, which does not compensate for the arm voltage oscillations and generates circulating current in each leg of 3-phase MMC. So this statement means that, let me show you the inner current control block diagram. This is basically inner current control block diagram. One of the current is D component of current, one other reference current is the Q component of the current. These two reference currents of the D component of the current, Q component of current are obtained from the outer loop controllers, and these two components ID and IQ are the values of the currents of the measured currents in the present MMC. Now basically the output of this inner current controller is the modulation index, MA. Now basically here from two reference signals we achieve at the output, and these two reference signals are basically modulating signals, which then basically operates and switches and perform the switching of the IGBTs or MOSFETs that are used in the MMC. Now in this direct modulation scheme, where the reference signal is taken directly, now this reference signal or modulated signal is basically sinusoidal in nature, and due to its sinusoidal nature, capacitor energy variation will be significant, and this reference signal will produce a more capacitor energy variation, and due to this it will also produce circulating current in each leg of the three-phase MMC. Now let me show you these reference signals mathematically, these upper and lower arm reference signals. These are the upper reference signal and this is the lower reference signal, and these are two complementary voltage reference for upper and lower arms. Alright. Now this paper presents a new method for reducing the circulating current by adding second and fourth harmonics in the upper and lower arm currents of an MMC. So the main concept and the major idea of this paper is to add second and fourth harmonic in this upper and lower reference signals. Now you see, if we add second and fourth harmonic in these two mathematical equations, you will get these two equations. Now in this upper reference signals, second and fourth harmonics are added, and lower reference signals, second and fourth harmonics are added. Now the author of this paper wants to emphasize that after adding these two harmonic, even order harmonics, second and fourth harmonic, the capacitor energy variation will reduce and circulating current will reduce in the system as compared to direct modulation as shown here. So author claims that addition of these two even order harmonics will result in decrease in the circulating current and will result in less capacitor energy variations. So let me show you the claim of the author and results. So you see, these are circulating currents. In direct modulation, when there is no addition of second and fourth order harmonic in the upper and lower reference signals, and this is the results when there is second and fourth harmonic added in the upper and lower reference signals. So you see circulating current is significantly reduced in this case, and you see these are the results for capacitor energy variation. If you take direct modulation, when there is no addition of second and fourth harmonic and direct upper and lower reference signals are taken, you see there is a lot of capacitor energy variation. But in case of proposed method, you see capacitor energy variations are reduced. So we graphically observed the benefit of the proposed method. Let us move ahead. Less capacitor energy variations are obtained by the proposed method compared to traditional direct modulation method. The proposed method is tested on a common symmetrical point-to-point MMC HVDC using vector current control strategy in PSK EMTD software. You see, these results are taken in this MMC based HVDC system, and this is the MMC basically, and these simulations are performed in PSK EMTDC software. So analytical and simulation results show the effectiveness of the new method in minimizing the circulating current, and arm voltage oscillation reduces as compared to the direct modulation approach. Alright. Okay, so here is the summary of this paper. The existing direct modulation technique generates sinusoidal arm currents that cause variation in capacitor energy. Because that direct modulation technique considers reference sinusoidal signals which are varying in nature. This varying in nature signal will cause variation in capacitor energy, will result into more capacitor voltage fluctuations. Basically, in the literature review, there are two methods used. One method is in which elimination of a higher order harmonics is done. You basically eliminate the higher order harmonics, which in turn increases submodule capacitor voltage ripples, but reduces the RMS value of arm current. This is one of the methods to reduce the circulating current, in which you eliminate the higher order harmonics, but this method will result into more submodule capacitor voltage ripples, but will reduce the RMS value of arm current, and certainly power losses will reduce, but at the cost of capacitor voltage ripple. Therefore, and the second way is injecting higher order harmonics inside circulating currents. Reduces the capacitor voltage ripple. So if you inject higher order harmonics in the circulating current, this will result in the reduction of capacitor voltage ripple, but due to the injecting of higher order harmonics inside circulating current, then certainly RMS value of arm current will increase, and this will result into more power losses. So these are the two ways basically in which circulating current can be controlled. But there is a trade-off between circulating current and capacitor voltage ripple problem in these two methods. So as already discussed, in some papers harmonics were injected inside the circulating current, which reduces the voltage fluctuation but lead to increase in RMS value of arm current, causing excessive power losses. So this is one drawback of this method. In another approach, differential current controllers were used to control the capacitor voltage fluctuations, which increase the hardware burden on the system, as well as additional controller specific adjustments. So some papers recommend additional controllers which overall increase the hardware burden of the system, therefore they are not recommended. However, in this research work, a new method is proposed to minimize capacitor energy variations by injecting even order harmonics to upper and lower arm currents, which restricts excessive negative currents in each arm of the MMC, leading to the presence of DC current components. So in this method, basically you add second and fourth harmonic in the reference signal, and if you add these second and fourth harmonic in the reference signal, then certainly due to addition of the second and fourth harmonics, now the shape of the arm currents will be different, and these arm currents will not be now purely sinusoidal in the nature, but overall their shape will be different, and DC current components will be having more higher value. Let me show you the effect of addition of the second and fourth harmonic on the waveforms of the current. So you see, this is upper arm current, this is lower arm current, and due to addition of even order harmonics, presence of DC current component increases, the arm voltage oscillations were also reduced. Arm voltage oscillations are now reduced. There are less capacitor energy variation as observed, and DC voltage is constant during part of period, which reduces the circulating current. So therefore circulating current is reduced, because this is not purely sinusoidal now in nature, but its waveform is changed. The DC current component, the peak value of arm current also reduces, the negative arm current is more flat at the bottom after adding the second and fourth harmonic. Alright. Okay. So this also results in reduction of circulating current and RMS value of arm current inside each leg of the MMC, which is evident from analytical and simulation results. So using this proposed method, you get both advantages: reduction in circulating current and at the same time reduction in the capacitor voltage fluctuations. So both advantages are obtained simultaneously. But in literature review, you were getting trade-off between the circulating current and capacitor voltage ripple in previous methods. The proposed method is implemented on point-to-point MMC HVDC test system based on a non-linear AVM model using the vector current control method. Vector current control method I will explain sometime. The strength of this paper is that it has explained basic mathematics of mathematical modeling of the MMC very well. It has explained MMC control system vector current control principle in a very simplified manner. Now these are the mathematical equations of the differential current. You see, differential current consists of the circulating current and basically this component, which is twice the fundamental frequency, this must be suppressed. This component must be controlled in order to reduce the power losses, in order to make the system stable. The circulating current should be controlled. Alright. So these are some results. The reference active power with reference power is 1000 MVA from terminal T2 to terminal T1. DC voltage, this is you see that both MMC operate at 0.96 power factor and generate 40 MVAR to meet the required reactive power demand at the AC side of HVDC system. Reference DC voltage 640 kV. These are the upper conductor and lower conductor currents. This is a reference signal without having direct modulation and no addition of second and fourth harmonics. These are the results after addition of second and fourth harmonics. And E and F are the upper arm current and lower arm current after the proposed addition of second order and fourth order harmonic, and these are the currents waveforms which are based on the direct modulation scheme, and these are more steeper and better in the shape. You see, advantages: circulating current is significantly reduced in the proposed direct modulation method as compared to direct modulation. Capacitor energy variation is also reduced in the proposed method. RMS current is significantly reduced. It is 0.65 kA, whereas in direct modulation it is 0.75. Differential current is also reduced in proposed direct modulation, which is 0.2. Otherwise, in the direct modulation it was 1 kA. So, overall, we observed that the proposed method seems to be better than direct modulation. Thank you very much for the listening. Thank you. I would like to mention here one more paper which is from the same author, but there is a little modification in methodology, and the way of proposed method is a little different. He names it as flat bottom current method, and the purpose is to reduce the capacitor voltage ripple reduction. The purpose is same: reduce the capacitor voltage ripple, reduce the circulating current, but this time instead of adding second and fourth harmonic order in the reference signal, he has added second and fourth harmonic in the current equations, in the equations of the current in the current signal, and he names this method as flat bottom current method. Let me show you the equations. These are reference signals, as you see. Now you see, he has added second and fourth harmonic, even order harmonics in the leg currents, leg 1, leg 2, leg 3. There are 3 legs in the MMC as we know. So he has added second and fourth harmonic in the leg, and this method he names it as flat current, flat bottom current method. So these results are same. The power, active power is taken as almost, reference signal is taken as 1000 megawatt, reactive power is 40 MVAR, which is same. And you see, as compared to direct modulation, the proposed flat current bottom method has reduced capacitor voltage ripples. So you see capacitor voltage ripples in flat bottom current method is reduced, and as well as the oscillations in the DC voltages are significantly reduced in the flat bottom current method as compared to direct modulation scheme. So these two major results are focused in this paper, which is published in Electrical Engineering Journal in the year of 2021, and the same author is another paper which is capacitor energy variation in MMC using harmonic injection. Now this paper is also consisting of basically the same idea, but here in this paper it is compared the results for the pure sinusoidal arm current, means direct modulation, another addition of large second order harmonic, and then the third is the sinusoidal arm current with addition of second and fourth harmonic, and compare these three results. So the basic idea is similar in this paper, and these results, research papers, are output of his PhD research work, which is conducted by the same author. His PhD title is HVDC System Stability Study using PSK EMT DC. So his major focus in the PhD is control the circulating current, reduce the circulating current, capacitor voltage ripple problem. Thank you very much.